Mentioned, I am presenting on information flow control. Fundamentally, however, what I'm talking about is the trusted computing base and trying to reduce it. There's a significant security problem with kind of just the world as it stands right now, which is that both developers and users have to trust code to do what it claims to do, or to do what it's supposed to do. So let's look at an example of this, of an application that users and developers have to trust. This is Servo. It is a rendering engine and web browser. And fundamentally, what's happening here is a pretty typical web browsing session. A user uses a keyboard to enter in keys, and then those are combined into various data. You can see here that what's happening is the user is attempting to donate to the Red Cross, so they're providing their credit card information. And at the same time, they're making the dubious decision to go check out evil.com and see how well that's going. And they're trying to enter in their login info there. Now, fundamentally, if the program operates this way, this is fine. Maybe the user is being a little unintelligent and going to check out evil.com, but there's no information being leaked here. There's no actual problems. But what if it doesn't operate this way? What if it looks more like this, where instead of the data flowing through the right streams and then it winds up getting sent to the right place, what if instead there's some other chunk of code that developers aren't aware of that just directly sends the information, all information, to evil.com? Or it goes through the networking but still sends it to evil.com. Developers have to trust that this pretty bad violation of confidentiality won't happen. And Servo's computing base is massive. Servo is over 1 million lines of code. So the trusted computing base for this example is insanely and impractically large. Now, to make matters worse, this is what real instances of this problem would look more like. It's not just the Red Cross and evil.com. The user might also have Google and Amazon and Twitter and another website and another and another and another. Just speaking practically, I've seen a lot of professors' computers at times in the middle of class where if they only have 10 tabs, it's impressive. So the number of tabs can be quite large, and more pointedly, it can't be known at compile time. It can only be known at runtime how many different tabs, different sessions you have active at once. Fundamentally, this is an information flow control problem. We need to limit what information can flow where. There have been decades of work on this problem, but it's still, in many ways, an unsolved problem. A couple of ways you could try to do this just don't work. Static analysis leads to numerous false flows, so trying to do a whole program analysis is impractical. And access control doesn't actually make the software trusted. You still have to trust the software to follow the access control policy. This is type-based information flow control. In other words, the type is changed. So instead of the type being a key, instead now the type is a key bundled with an attached label. You can see the upper label is R cross or Red Cross. The lower label is evil for evil.com. So this is signifying the information should only go to the proper destination. If this works, then the illegal flows that we don't want to happen, the breaches of confidentiality that developers have to trust won't happen, are automatically prevented. And this would reduce the trusted computing base down from the entire 1 million lines of Servo down to just the networking segment, down to a much smaller, much easier, much more practical to audit segment of the code. Now, there's a practical problem with this, which is that information flow control doesn't apply to unmodified languages in most work. However, I did very pointedly say most work, and there's a reason for that, which is my next slide. Last year, I presented, along with my fellow authors, the work Cocoon at OOPSLA'. Cocoon prevented static information flow control in an off-the-shelf language and compiler, which is Rust. So, okay, this kind of leaves the obvious question, why am I here now? We solved this last year, didn't we? Well, unfortunately, Cocoon had a couple of significant limitations to it that required addressing. First is that Cocoon was only static. It could not do dynamic information flow control. So in the example that we discussed, where you have Google and Amazon and all these other tabs, Cocoon couldn't handle that. which means Servo couldn't actually have this policy enforced that developers would feasibly, theoretically, like to have enforced. And in addition, Cocoon had a very limited evaluation. The evaluation was closer to a proof of concept than a complete, thorough, comprehensive one. And if I'm trying to argue for practical information flow control, I need a real evaluation. If a developer wants to trust that information flow control is practical, they need to know there's good evaluation, there's good tests behind this. Our solution is Carapace. Carapace provides exactly the same benefits as Cocoon and more. It still provides static information flow control. If there's a compile time known policy that can be enforced, Carapace can enforce it at compile time. It is still off-the-shelf language and compiler for Rust, and in addition it adds dynamic information flow control so it can handle runtime policies, and it provides a thorough, comprehensive evaluation. Now, part of evaluation is metrics, which I will get to in a moment, but part of evaluation is also that we could do what we said we did. In particular, Cocoon and Carapace both had a relatively challenging programming model. So how feasible is it to really use this, to use this in real programs, not just contrived toy programs that maybe we wrote? So we wanted to retrofit real practical programs and change them to use Carapace. So what did this retrofitting process look like? This is what it looked like. The start is to bootstrap with Carapace. For a quick bit of background, Carapace is implemented as a Rust library. So for a developer to use Carapace, they would import the library, change the types to be protected, and then enter the middle block here. In the middle block, the developer would fix compiler errors using three things, which I'll cover in the next slide: secure blocks, wraps, and unwraps. Fixing the errors using these would lead to more errors as the information flowed down, if you will. Fixing these would lead to more errors, more errors, more errors, and repeatedly until eventually, hopefully, the developer would be done. Now, as you may be able to tell, that middle block covers a lot. So what exactly does this look like in practice? This is a real example of code from Servo. This is pulled directly from Servo, no changes, no modifications to it yet. It computes the length of a secret UTF-8 and UTF-16 string. The string is text, highlighted in bold there. And in our particular flow of information, the flow that we wanted to have, text should be a protected secret. It shouldn't be legible, it should be confidential. Because it's secret, that means its data would also flow into this UTF-8 lin value, which means it should also be secret as well. We, in retrofitting Servo, wanted to make this use Carapace, so we needed to meet these constraints. We needed to somehow make this work. The first step is to put it inside a secure block. Secure blocks are the only places that protected values can be accessed, as enforced by Carapace itself. If a developer marks a value as protected, it can't be accessed anywhere except a block as enforced by Carapace. The code won't compile. Carapace enforces this using Rust macros. Developers need to, when doing this, provide what labels they want the block to have, or in other words, what labels the associated data that they're allowed to read are. Labels are in two flavors, static and dynamic. Static labels come as types in Rust, and dynamic labels come as expressions, which will be evaluated at runtime so that they can then be analyzed and runtime policies can be enforced. So the first step is this, just add the block. The second step is using unwrap and wrap. These kind of do what they sound like they do. Unwrap removes protection from something so that it can be accessed in red. Wrap rewraps it, reprotects it, so it can be treated as protected and secure and continue to flow through the program properly as developers and as we desire. Now, developers have to add these changes. They have to add blocks, they have to add unwraps, they have to add wraps. But notably, without these changes, there will not be a violation of information flow control, there will not be a violation of confidentiality, the code won't compile. So developers have to make these changes, but the guarantees are enforced by Carapace regardless of what the developers do. The developers will either produce a secure program or the code won't compile. No insecure program will be produced. Now, We just covered the retrofitting. So what did we retrofit? We retrofitted 3 real-world programs. All of these are programs that we did not write, that we found on GitHub. They are publicly accessible and able to be checked out yourself. The first is Servo, which, as I described, is a web browser and rendering engine. As of the time of creating this presentation, it was one of the top 30 projects on top 30 Rust projects on GitHub as ranked by stars. For this one, we enforced the policy of when a user types a key, it should only go to the tab they typed that key into. It's the policy that the motivating example showed of if you type in your credit card information, it should only go to the website you typed it into. Avail is a calendar availability finder, or in other words, you have 2 calendars, you want to find what's a shared time where there's an open slot here. The policy here was only the shared time should be made public, the entire calendar should not be made public. And finally is an active online multiplayer game called MK48.io. It's a little ship combat game. You steer your ship around and fire missiles at other ships and so on. The policy here was you should only be able to control your own ship. A malicious player should not be able to take over someone else's ship and, I don't know, crash it into an island or something. Now, as I said, part of evaluation is that we could do this. Well, we did this. All of these policies were enforced, all of them used Carapace, and all of them worked. So now, on to the numbers. There are 2 particular numbers that we presented. Changed code we presented because it represents roughly how much we had to write and change in order to do this, so it represents, to a certain extent, effort as a rough indication. For all of these, as you can see, changed code is under 3%. For a larger program like Servo, it is in fact very low at 0.3% of the million lines. And then for all of them, we also measured runtime overhead. And for all of them, runtime overhead was undetectable. More results presented in the paper in more details. But in conclusion, Carapace provides practical information flow control and demonstrates its use in retrofitting real-world Rust programs. Thank you.
We have a couple of minutes for questions.
Hey, thank you. Very nice talk. I wanted to, maybe I didn't understand exactly. So how do you know that the policy was enforced, in the sense that how do you know that it prevented a bug that was possible in the first place?
I'm sorry, repeat the second half of that. I caught, how do you know that the policy was enforced?
Yes, how do you know that the policy was enforced?
Yes. So let me go to the right slot. So here, as you can see, the block here, this is you can see the exclamation point there at the end of the first line. This is a macro. Carapace defines a set of macros that will transform the code inside the blocks, essentially. As part of that, there are type checks, there are runtime checks. It will add in various checks to enforce it, make sure it happens. So all the checks will be enforced. All the constraints will be enforced via checks. The checks just aren't ones the developers write. They're automatically generated by Carapace itself.
Thank you very much.
Had mostly the same question, but I guess as another one, it seems like some of the changes, like wrap, unwrap, kind of painful, but also could be automated.
Kind of painful, could be what?
Automated? Like if it's a secret block and the secret variable always has to be unwrapped to be accessed, why doesn't the macro do it for me?
Yes. Long story short, my lab mate has actually been working on that somewhat recently. One of the things he's run into is, in particular, in figuring out where to add where to define the edges of the block, he found that it was relatively tricky to figure out how to do that because, to a large extent, where do you define the start, where do you find the end? For a human, it's pretty intuitive, it's pretty straightforward. In automatic synthesis, he found that it was quite challenging for computers to do in a way that generated workable code.
Can I ask another one? Do you do anything with like declassification at all?
Yes, I omitted it from the slides because of time, but yes, declassification is provided for. We provided a trusted block instead that has to be audited, but that's how you would do declassification.
Let's thank Vincent again.